When the neutral wire was disconnected while the breaker was on, a specific sequence of events likely unfolded. Firstly, a loss of the neutral path occurred. The neutral wire is crucial because it provides a dedicated route for electrical current to return to the electrical panel. When this neutral wire is disconnected, it effectively breaks or removes this essential return path. Secondly, a circuit imbalance resulted. In this scenario, two 20-amp circuits were sharing a single neutral wire. When the neutral connection was severed, the current that would normally flow back to the panel through the neutral was now forced to find an alternative route. This meant that the current from both circuits was compelled to flow through the remaining circuit that was still connected, creating an imbalance in the electrical system. Thirdly, this led to an overload on one circuit. As the current flow increased significantly on the remaining connected circuit due to the absence of the neutral return path, it exceeded the circuit's design capacity. This overload stressed the wiring and components within that circuit. Fourthly, the conduit was improperly used as a ground. The electrical conduit, which is the metal pipe housing the wires, was being utilized as the ground connection. This is generally considered an unsafe and often ineffective grounding practice. When the neutral wire was disconnected, the conduit failed to provide a reliable and sufficient path for the return current to safely flow back to the electrical panel. Fifthly, a voltage surge occurred as a consequence of the aforementioned issues. Due to the combination of the imbalanced current flow and the absence of a proper and effective ground path, a voltage surge manifested within the electrical system. This surge represents a sudden and significant increase in voltage levels beyond the normal operating range. Sixthly, this voltage surge resulted in damage to the power strips. The excessive voltage stressed the components within the power strips, leading to their failure. The power strips were not designed to handle such high voltage levels and succumbed to the surge. Seventhly, one computer sustained damage due to the same voltage surge. Similar to the power strips, the computer's internal components were vulnerable to the excessive voltage, resulting in damage and potential malfunction. The fundamental reason why this happened is that the neutral wire is absolutely essential for completing the electrical circuit and providing a safe and reliable path for the current to return to the electrical panel. When this neutral wire was disconnected, the normal current flow was disrupted, leading to an overload on one of the circuits and the subsequent voltage surge. The reliance on the conduit as a ground, which was not a proper and safe grounding method, failed to provide a sufficient path for the errant current, ultimately resulting in damage to the power strips and the connected computer. It's extremely important to understand the safety implications of such practices. Using the conduit as a ground is a hazardous practice that can lead to serious consequences. It typically violates established electrical codes and regulations. This unsafe practice puts both people and equipment at significant risk by increasing the potential for electrical shocks, fires, and other accidents. Proper grounding is absolutely essential for ensuring electrical safety. It provides a low impedance path for fault currents, helping to protect against electrical hazards and equipment damage. Now let's delve into the technical aspects in more detail. Firstly, the function of the neutral wire in a balanced electrical system is to carry the imbalance of current between multiple hot wires. In a perfectly balanced system, the current in the neutral would be 0 amps. However, real-world loads are rarely perfectly balanced, hence the need for a neutral wire. Secondly, when the neutral is disconnected, the voltage on the two 20-amp circuits can become unstable and unpredictable. The voltage on one circuit may rise significantly while the voltage on the other circuit drops. This is because the loads on the two circuits are now in series with each other, and the voltage divides between them based on their impedance. Thirdly, the use of conduit as a grounding conductor is permitted under specific circumstances in the National Electrical Code, or NEC. However, it requires that the conduit be properly installed and maintained to ensure a continuous and low impedance ground path. Simply relying on the conduit without proper bonding and connections is not a safe or code-compliant practice. Fourthly, the voltage surge that occurred when the neutral was disconnected can easily exceed the voltage rating of sensitive electronic components in power strips and computers. These components are typically designed to operate within a narrow voltage range, and any significant overvoltage can cause them to fail. Fifthly, the lack of a proper ground path can also exacerbate the effects of a voltage surge. A properly grounded system provides a path for the surge current to flow back to the source, which helps to limit the voltage rise and protect equipment. Without a good ground, the surge current can find alternate paths through sensitive electronic equipment, causing damage. Sixthly, the fact that the computer was damaged even though it was turned off suggests that the power supply was still connected to the electrical system. Even when a computer is turned off, the power supply typically remains energized to provide standby power for features such as Wake on LAN. This means that the power supply is still vulnerable to voltage surges. Seventhly, to prevent this type of incident from occurring in the future, it is essential to ensure that all electrical circuits are properly wired and grounded in accordance with the NEC. This includes using appropriately sized conductors, providing a dedicated neutral conductor for each circuit, and installing a reliable grounding system. Eighthly, regular inspections and testing of electrical systems are also crucial for identifying and correcting potential problems before they cause damage or injury. This includes testing the continuity of grounding conductors and checking for voltage imbalances on neutral wires. Ninthly, when working on electrical systems, it is always important to follow proper safety procedures, including de-energizing circuits before working on them and using appropriate personal protective equipment. Tenthly, if there are any doubts about the safety or condition of an electrical system, it is always best to consult with a qualified electrician. They have the knowledge and experience to identify and correct potential hazards. Now, let's elaborate further on the specific code violations that may be present in this scenario. One potential violation is NEC section 250.4 A5, which requires that the grounding path be permanent and continuous. Using the conduit as a ground without proper bonding may not meet this requirement. Another potential violation is NEC section 300.3 B, which requires that all conductors of a circuit, including the neutral, be installed together in the same raceway or cable. Sharing a neutral between two circuits may not meet this requirement, depending on the specific wiring configuration. Furthermore, NEC section 310.15 addresses ampacity and requires that conductors be sized appropriately for the loads they serve. Overloading a neutral conductor by sharing it between two circuits can violate this requirement. It's also important to consider the potential for harmonic currents in this scenario. Harmonic currents are non-sinusoidal currents that can be generated by electronic devices such as computers and power supplies. These currents can add up in the neutral conductor, potentially overloading it even if the fundamental currents are balanced. The NEC addresses harmonic currents in section 220.61, which requires that the neutral conductor be sized to carry the maximum unbalanced load, including any harmonic currents. In addition to the NEC, there may be other local codes or regulations that apply to this installation. It's important to check with the local electrical inspector to ensure that all work is in compliance. To further clarify the concept of impedance, it's the total opposition that a circuit presents to alternating current. It includes both resistance and reactance. In this case, the loads on the two circuits, such as the computers and power strips, have different impedances. When the neutral is disconnected, these impedances are placed in series and the voltage divides between them proportionally to their impedance. The circuit with the higher impedance will experience a higher voltage, which can lead to damage. The ground fault current path is the path that fault current takes from the point of a fault to the source of the electrical supply. A low impedance ground fault current path is essential for allowing overcurrent protective devices, such as circuit breakers, to quickly trip and clear the fault. A high impedance ground fault current path, such as relying on a conduit without proper bonding, can limit the fault current and prevent the overcurrent device from tripping, which can lead to overheating and fire. The proper way to ground an electrical system is to install a grounding electrode system, which typically consists of a ground rod or a ground plate that is connected to the earth. The grounding electrode system is then connected to the electrical system through a grounding electrode conductor. All metallic enclosures, such as conduit and equipment housings, must be bonded together and connected to the grounding electrode system. This creates a low impedance ground fault current path and helps to protect against electrical shock and fire hazards. Remember to consult with a qualified electrician for any electrical work to ensure it is done safely and in accordance with all applicable codes and regulations.